Hey everyone, welcome back to Engineering Education. For this next problem, suppose that we have a three-phase Y-connected system, and this system is 100 MVA and has a power factor of 70%, and this power factor is leading, and the line voltage is 13.8 kilovolts. Here we're asked to find the phase current, both the magnitude and direction of this system. And lastly, we're asked to find the phase current, again, magnitude and direction, if the power factor was lagging. So, as always, pause the video, give it a shot, and we'll go over the answer in a bit. So, to go ahead about solving this, we need to know the difference between the Y systems and the delta systems. Now, I'm going to include the delta system here just for completeness. So, for Y, the phase voltage, which I'm going to denote like so, is equal to V line divided by the square root of 3. And for a delta system, the phase voltage is equal to the line voltage. And for currents, for a Y-connected system, the phase current is equal to the line current. And the phase current here for a delta system is the line current divided by the square root of 3. Now here we're given power factor. So we can get the power factor angle from this power factor. And so remember from last videos that power factor angle is equal to the apparent power angle, which is equal to the impedance angle, which is equal to minus the current angle. Now we're assuming here that we're using a reference voltage angle of 0. So we're assuming theta V is equal to 0. And from here we can get our power factor angle. We're just going to denote it as theta is equal to the arc cosine of the power factor, where the power factor is 0.7. So if we do the arc cosine of 0.7, we get 45.6 degrees. Now we need to determine what the sine of this angle is. So if you recall from the last videos, in order to have a leading power factor, we said that we needed a positive theta I. And a positive theta I means that we need a negative theta S, theta Z. And so, because we have a leading system, this angle is actually negative. And so now we can find the magnitude of the current. So to do this, we can start with our definition of apparent power, which is the square root of 3 times V line times I line. Rearranging this equation for I line, we get the following: S divided by the square root of 3 V line, where S is given at 100 MVA and V line is given at 13.8 kilovolts. So if we plug these numbers in, 100 MVA divided by the square root of 3 times 13.8 kilovolts, we get 4.18 kiloamps. And we know from the basic property of the Y-connected system that I line is equal to I phase. And so that gives us the magnitude of the phase current, and the direction is simply just the positive theta I. Right, so if we look here, so it's just going to be the power factor angle at 45.6 degrees. So that gives us that the phase current is equal to 4.18 kiloamps at an angle of 45.6 degrees. Let's do it in green. And so what if this power factor was lagging instead of leading? The magnitude stays the same, whether it's leading or lagging, and the only thing that changes is the sign on the current angle. So if we were to have a lagging system, then we would have negative 45.6 degrees. So just to write it out, it would be 4.18 kiloamps at an angle of negative 45.6 degrees. So this leading versus lagging thing, magnitudes always stay the same and just angles change. And they're always going to follow this relationship here. So I hope you guys enjoyed this. If you did, please leave the video a thumbs up, and I'll see you guys in the next video. Until then, enjoy engineering.